Recording. All right. Today we will look at the EM algorithm. The EM algorithm, and we'll look at. So the EM algorithm can technically be quite complex, but we will look at the EM algorithm for mixtures, and in this case, Gaussian mixtures. Okay. So what we're going to do is we're going to represent, we're going to generate data from a mixture of multivariate Gaussian distributions. Okay, and so the way our data is going to be generated is first we're going to select a random a value representing which cluster the data point comes from. Okay, so it's either going to come from cluster 1, 2, or 3, and we give it a probability vector. Okay, and so in this case, I'm going to say half of my points come from cluster 1, 0.3 come from cluster 2, and 0.2 come from cluster 3. Okay, so this is just these are just arbitrary values that I've chosen for our example that we're going to kind of work through. But the idea is you just have some vector alpha of length k representing kind of the mixture components, the k components that are being mixed together and their mixture probabilities. All right, and then once you've selected a value from the component, then what we'll do is we will generate a random value from that particular distribution. So you have a multivariate Gaussian distribution for each of these components, and so here we've got a normal distribution centered at our first component is a multivariate normal distribution centered at 0, 0, and has this variance covariance matrix. So variance of 9 and no covariance here. Okay. Then component 2 has this component mean 4, 4, and this variance covariance matrix. Okay, so its variance is 1 for components 4 and 4, but and there's high covariance between them. Okay, so x1 and x2 have high covariance between these two sides, covariance of 0.9, and their relative variance, and their variance is 1. Okay, and then component 3 is centered at -4, -4. Okay, and it is its variance is 2, and it's got a negative covariance of -1 here. Okay, so it'll kind of negative covariance there. And if we want to kind of represent the mixture distribution mathematically, this is how we would do it. Okay, so we've got kind of the overall probability of some point x given theta is going to be equal to basically the sum of these mixtures here. All right, and so each x value exists in two-dimensional space. Okay, so here we've got a multivariate Gaussian distribution. Okay, which again exists in two-dimensional space, and so x is a point in 2D space, and this thing theta collects all of the parameters from all of the different mixtures. Okay, and so the parameters include this vector alpha, and all of the means mu, and all of the variances sigma. Okay, so theta collects all of these things: the mean, the mu's, the sigmas, and the alpha together. All right, so we're going to say the probability of x given theta is going to be equal to the sum of these mixtures, okay? And so we've got the alpha sub k's are the mixture weights, okay, representing the probability that x comes from component k, right? And so we kind of see this already. The alpha values have to add up to 1, okay, and they represent basically the probability that a value comes from a certain component, okay. And then p sub k, this is going to be your PDF, okay, your probability function, probability density function, or mass function. In our case, it's the multivariate Gaussian PDF, okay, and the PDF is defined by kind of its parameters. And so in this case, theta sub k represents both the mean vector and the matrix, variance matrix sigma, okay? So this is the generic form for a kind of a mixture, any kind of mixture distribution. And here we're specifically going to be using a mixture of multivariate Gaussians. So here I've got p sub k, and the theta sub k's represent the parameters of that distribution, okay? And then z sub k is kind of the indicator variable to indicate which component it comes from. If it and so this is going to be a vector of zeros and ones, where if the x comes from component 2, that vector is going to be 0, 1, 0. So it's going to be zeros for everything that is not the component, and it'll be a 1 for the component that it does come from. Okay, and so this will be so this is how we represent the mixture distribution. Okay, and so here is how I would maybe generate the data in R. So here I'm going to just kind of specify the properties of the individual components. So here I got alpha, and that's going to be 0.5, 0.3, 0.2. And then the mean of component 1 is 0, 0, and the sigma of component 1 is, matrix 9009. The mean of component 2 is 4, 4, and the variance matrix of the second component is 1.9.91. And then lastly, we've got -4, -4, and 2, -1, -1, 2. Okay. So we get, kind of our 2 by 2 matrices here. I'm going to collect them all in a list. I've got the means collected in the list, and the sigma matrices collected in the list as well. And then to generate my data, I'm going to use library multivariate norm, right? And I'm going to store all of my values in an X matrix, okay? Currently three columns and 1,000 rows here. And what I do is for each row, first I'm going to select which component it comes from. Okay, so I'm going to use sample, and it's going to sample either 1, 2, or 3. Okay, sample 1, 2, or 3. We just want one value sampled from 1 through 3, and then we're going to use my vector alpha to represent kind of the probability of each value. So it's going to draw 1 with probability 0.5, and 2 with probability 0.3, and so on and so forth, as defined with that vector alpha. And then once we've selected the k, then we're going to generate a value from the multivariate normal. So we're going to get so I use RMV norm, and we use, I'm going to ask for one value from the multivariate normal, okay? And it's going to have a mean using double bracket k. So it's going to select either mean 1, mean 2, or mean 3, depending on the k that got selected here. Okay. So mean 1, mean 2, mean 3, or sigma 1, 2, or 3 as well. Okay. And then so this will be a length 2 vector because the multivariate normal has is two-dimensional here. Okay, and then I'm also going to store the class assignment K, or the cluster, which cluster it came from, K. So that all gets stored in our in the row X, the X row I. All right, and so that's how we would generate the mixture, and this is what it would end up looking like. Okay, so we can kind of see, but it's kind of hard to see, right? So we have a cluster centered at 0, 0. We have a cluster centered at 4, 4 that exhibits high covariance. The cluster centered at 0, 0 has no covariance, but high variance, right? Variance of 9, so it's very spread out. Okay, the cluster at 4, 4, its variance matrix was 1.9.91, so it exhibits high covariance. Okay, and it's concentrated in this corner. And then the other cluster is centered at -4, -4, had variance of 2, -1, -1, 2. Okay, and so it's got some negative covariance here, and it angles a little bit this way. All right, so so this is how the EM algorithm would see the data. The clusters are not labeled, and all the data just kind of shows up like this. And if I told you identify 3 clusters in here, this would be your job, and you'd try to figure out where the clusters are. Here, because we generated the data, we know the actual cluster that each data point came from. So we can see all of these points came from the red cluster, and these points came from the green cluster. But this also, if you look, also has a mix of some points that came from the black cluster, because the center, the cluster in black, has high variance. So yeah, some of the values got mixed in over here, and somewhat. So these points over here are a mix of green and black. Okay, but we don't know that, right? It just looks like this. And if we were to try to use k-means clustering would not do well in this for this data set. Okay, because k-means clustering uses Euclidean distance only. So it's going to only is going to say, like, this point right here, right? So let's say we know that there's a centroid right here. Okay, the centroid right here will say if this point belongs to this centroid, or this cluster right here, it looks at this distance, and it basically says this point over here is just as likely, or is more likely, to be part of this centroid, or should definitely be assigned to this centroid, because its distance is shorter. The distance from here, this point here, to the centroid here is shorter than the distance to this point way over here. Okay, but we can see that, yeah, this point is not going to come from this thing, because if we take into account kind of the variance covariance matrix there, and the spread of the points from this red cluster here, we can say, yeah, it's very unlikely to come from this thing, right? We would draw kind of an oval that goes around here, and we would say, yeah, this point does not belong. But does it make sense that these points belong? Sure. These points can belong, but this one does not. Okay, and so k-means clustering is not going to do well, because k-means clustering uses Euclidean distance, and only Euclidean distance, and says, yeah, if it's close in this direction, it's going to belong to this cluster. Okay. Similarly, if we look at this point right here, okay, k-means clustering, if we say there's a center right here and a center over here, center at 0, 0, and a center at -4, -4, k-means clustering would look at this point right here and say, oh, it definitely belongs to the centroid over here, because the distance to this cluster is shorter than the distance to the one that belongs over here. Okay, but again, what we want to do is we want to be able to take into account kind of just the spread of the distribution. We can say, well, you know what, this one has the central cluster has a very high variance, and so maybe we want to assign this point to the central cluster and not just to the cluster that's closest by, right? So k-means clustering has got some limitations in that it only uses Euclidean distance, right? You know, we might say, what about this point? This point that kind of like visually we can see there's a kind of a cluster here. And what about a point like right here that looks like it's kind of at the borderline between, you know, does it belong to this cluster? Does it belong to the central cluster? It's a bit of a mystery. It's hard to fully designate and say, does that belong to one cluster over the other, right? So how would we designate that point? Like, how would we assign these, right? So k-means clustering says just definitely you want to assign it to assign each point to the cluster with the nearest centroid, okay? But how should we assign the points here, right? We're not going to say just use the nearest centroid. We want to use something a little bit more subtle. And how should a point be assigned? Should it be assigned to this? If we say there's a cluster in the middle and there's a cluster over here, how should we assign this point? Okay. Well, the answer is you don't have to assign the points. What we can do is we can use a probabilistic assignment. Okay. So what we're going to do is we're basically going to use the Bayes classifier to get probabilistic assignments, right? So we covered the Bayes classifier a couple weeks ago, and you did it in your homework, or at least the naive Bayes classifier. And the idea there was, you know, you use kind of Bayes' rule and the likelihood and the prior and the marginal and all of that. And what we're going to do is we're going to do that for each point. So in k-means clustering, it was you look at the different centroids, the distances to the centroid, and you'd say, this centroid is closer, therefore this point gets assigned to this cluster. And it's farther from this centroid, so it does not belong to that cluster. Here we're going to say, you know, what's the probability it came from this cluster? What's the probability it came from this cluster? And we're going to get a probabilistic assignment. So we might say this point is 80% cluster 1, 20% cluster 2, 0% cluster 3, or like maybe 80%, 19%, 1%, okay? Or it could be something like it is 50% cluster 1, 49% cluster 2, 1% cluster 3, or something like that, okay? So we're going to get probabilistic assignments, and we're going to call these membership weights, okay? And so the vector of probabilities, the membership weights will add up to 1. And so we're going to get a vector assignment that represent kind of the probability that it belongs to a certain cluster, right? And then once you have those membership weights, you know, these probabilistic assignments, then we're going to recalculate the parameters of each cluster distribution, right? So so we're going to, so each distribution here is a multivariate Gaussian, okay? And multivariate Gaussian needs to have a mean vector and a variance covariance matrix, right? And so, so once you have the membership weights, you're going to recalculate the mean and the variance covariance matrix of each cluster distribution, right? And we're going to do that kind of using a weighted mean and a weighted variance covariance matrix. And we iterate back and forth between reassigning the points using, I should say, between calculating the membership weights and then calculating the cluster, the parameters of the cluster distributions, okay? You can kind of think of this EM algorithm as a blend between k-means clustering and the Bayes classifier. So it's kind of like k-means clustering, except rather than doing strict assignments based on the nearest centroid, you're going to use the Bayes classifier to get your probabilistic assignments. And then with the probabilistic assignments, you're going to calculate the weighted parameters of the distribution. Okay, that kind of maximizes those likelihoods. So so yeah, so you iterate back and forth between calculating the membership weights, which is kind of like reassigning the points, and you're gonna and iterating between recalculating the parameters of the cluster distribution, which is kind of like recalculating your centroids. So let me talk about calculating these membership weights. Okay, so this is what we call the E step, the expectation step. Okay, this is calculating the membership weights. And so here we use a Bayes classifier, right? So the weight that point I belongs to cluster K, the weight that point I belongs to cluster K can be expressed as the probability that the Z, that binary vector, zi sub k is equal to 1, and basically everything else is 0, right? So zi sub k, z sub ik is 1, given basically the values of x and theta. And so we would say this is the likelihood times the prior divided by the marginal, okay? And so here we've got the likelihood, which is going to be our multivariate normal PDF, and then the alphas, which will be our prior, okay? And then the marginal, this bottom is going to be just the, much like the Bayes classifier, is the numerator summed across all possible clusters, right? So if you understand the Bayes classifier, this part, I hope, is okay. So let me just delve into a little bit of this. So we'll talk about the alpha part first, okay? So the alpha k is kind of our prior probability. It comes from the previous iteration, all right, or your initial values, okay, that a point belongs to cluster K, okay? And you can think of this as the proportion of points that are assigned to cluster K, right? So it's going to be kind of like the number of points assigned to cluster K divided by the total number of points. So it's kind of like the proportion of points assigned to cluster K, right? Except this number of points is not truly the count of points assigned to K. It's not an integer. It's not like we said, oh, 23 points are assigned to K, okay? We're getting this n sub K value by adding up the membership weights, right? So it could be like these 20 points have a 99% probability of belonging to cluster K. So therefore, you know, let's say they belong to cluster 1. Okay, these 20 points have a 99% probability. So technically, if that's the case, then n sub k, so n for cluster 1 would be, you know, 90.99 times 20, so it would be like 19.8, right? So your n sub k would be 19.8, and that's not an integer. It's basically the sum of the membership weights, the sum of the weights that belong to that kind of that cluster. Okay, so it's not necessarily a count. It's not necessarily a count of the points. Okay, so you can think of it as kind of the sum of these membership weights here. And then as far as the p sub k goes, that's going to be the probability density function, right? So it's the PDF of x, right? So x is your the x, the two-dimensional vector that we have, and we're asking what's the probability of getting that given your mean and sigma matrices, okay, or your mean vector and sigma matrix. So we're asking for those pieces, and so this can be found using the multivariate normal density, right? So I mean, you can plug it into the PDF, right? But we're going to make our lives a lot easier by using R's function, dmv norm. Okay, so we're going to say what's the density from the multivariate normal of this x value, given that the mean is this and the variance is this, right? So that's going to be the likelihood. What's the likelihood of getting this particular value using these things? And so if you think back to your Bayes classifier homework, you'd have to do this for each component, right? So you said, what's the probability of getting these values if the flower is setosa, or what's the probability of getting these values if the flower is virginica or versicolor or whatever it was, right? And so here we would say, what's the probability of getting this two-dimensional point if it came from cluster 1, or what's the probability of getting this two-dimensional point if it comes from cluster cluster 2 or cluster 3 or something like that, okay? And so we're going to calculate this using DMV norm, right? So that's, and the marginal, I didn't make a slide for that, but you're going to basically calculate the numerator across all possible clusters, and you would sum them up, okay? So yeah, the likelihood, which is based on the multivariate normal density, and that's just because that's what we're using here. And then alpha sub k is kind of the quote-unquote proportion of points assigned to cluster K, but it's but again, it's using the weights, so it's not an integer. It's using the weights. Okay, so that's how we do the assignment of points. Okay, and then what we do now, the next step is that we are going to calculate the recalculate kind of the parameters of the distribution using kind of your mean and variance, calculate your mean vector and variance matrices, okay? And so so here what we do is we're going to calculate basically the centroid of a cluster using a weighted mean, okay? And so I just take each x and I multiply it by its membership weight, right? So these are this is the probabilistic assignment. We said, x belongs to cluster 1 with 80% probability, or it belongs to cluster 2 with 19% probability. We're going to take that x and we're going to multiply it by either 80% or 19% or whatever. And we're going to get basically the weight multiplied by the x. And then we're going to add those up and divide by, again, the quote-unquote total number of points assigned to cluster K. Total number of points, again, being the sum of the weights, all right? If you look at this is actually identical. The formula for calculating the centroid is identical to the formula for calculating the centroid in k-means clustering. The only difference is that in k-means clustering, this is z sub ik. Z sub ik was binary. It was either 1 or 0, meaning that this point contributed to the weight or it did not, right? All right, contributed to the centroid or it did not. And here we're allowing this w to be a value between 0 and 1, okay? So it can contribute not fully, but like maybe partially, or it can contribute maybe not nothing, but only a tiny bit. So so we get the means this way, okay? So we're going to get mu sub k as such. And then over here, we calculate the variance matrix, okay, using kind of the formula for the variance, which is basically x minus mu times x minus mu transpose, right, in vector form. If I had gotten rid of this, if I get rid of this weight thing, this is pretty much the formula for the variance. Technically, the variance would have 1 over n minus 1, okay? But this would pretty much be the formula for the variance. And this is basically your maximum likelihood estimate of the variance matrix based on your data, okay? And here it is it's weighted again based on the class assignments or the cluster assignments. So we say, if we know x belongs to this cluster, or if it has a high probability of belonging to the cluster, we're going to give it this weight will be high when we calculate its component contribution toward the variance. If a particular X has a very low probability of belonging to a cluster, we're going to give this a small value, and it will contribute very little towards the total total matrix here, the variance matrix. All right. Okay, how does this feel? Do we feel like this is okay? So again, you can kind of, if you understand k-means clustering, the idea of finding the centroid, associating the points to the nearest centroid, it's very similar to that, except we're doing probabilistic assignments. And then when we calculate the quote centroids and the parameters of our distributions, we're using basically weighted versions of these things. So based on the probabilistic assignments, we're getting weighted versions of the assignments. So we're going to get weighted a weighted mean and a weighted variance. And then when we do the assignments, we're getting probabilistic assignments. Okay, so we will iterate between recalculating the membership weights and then recalculating the mean and variance. And then we go back, recalculate the membership weights, we recalculate the mean and variance. Okay, and you go back and forth. All right, so if that makes sense, you know, give me a green check. Otherwise, you know, raise your hand or ask a question in the chat. Let me give you the first quiz answer. Today it is 8th week Friday. Our first quiz answer is B. B as in boy, B as in bear. First quiz answer is B. Okay. All right. Okay. Well, some of you guys gave me green checks. I hope the rest of you guys are okay. And so let's kind of take a look. All right. So here is kind of our data, not labeled. This is how we see it. And once again, these are the true assignments because we generated the data, and so we know which exactly which component each observation came from. Okay. But of course, in real life, that is unknown to us. We don't get to know. Right. But this is where they came from. All right. So I'm going to just start off with just a arbitrary set of mixing parameters, okay, which I'm going to just say are about 1/3 each, 0.33, 0.33, and 0.34, so it adds up to 1. And then here I just start off with arbitrary mean locations, and then I'm just using basically the equivalent of the identity for my sigma matrices, right? And then as far as the rest of the slides go, I've hidden my code. I've intentionally hidden them because for your homework assignment, I'm going to make you basically code up the EM algorithm, and so I've intentionally hidden it, so just so you get the satisfaction of doing this as part of your homework, okay? And so anyway, this is where we start off. These are our initial assignments here, and these circles represent kind of where the kind of the distributions that exist, and so you know, they have relatively small variances, and so so this is what we have, and then we just say what's the probabilistic assignment here, okay? And so we assign basically the points to based on the probability that it belongs to each cluster, because each cluster has the same variance. It's going to be equivalent to like which cluster has the same. It has the nearest centroid here. This graph is a tiny bit misleading. The plot's a little bit misleading because when I color the dots, I can only color them with one color, okay? So a dot either gets colored green, or it gets colored black, or it gets colored red. I don't have, I can't color a dot with more than one color. But the truth is that like these points right here that are kind of at the border between red and black, they are, this point right here is probably something like 51% red, 49% black, Okay, so everything gets a probabilistic assignment. So this dot right here is probably 51% red, 49% black. This dot right next to it, but colored black, is probably 49% red and 51% black. Okay, so everything gets a probabilistic assignment. You know, when I color the dots, I'm only able to say this one's red or this one's black, and the way I colored them was just saying, you know, which probability is the highest, and color it according to the highest probability. But you know, but the values are actually probabilistic. It's going to say something like, you know, 51% red, 49% black, or 49% red, 51% black. Okay, so and I think you probably experienced something like that when you were using the Bayes classifier for your iris data. You know, you'd get something like this. You know, I think a lot of the points ended up something like 99% virginica or 99%, you know, setosa. But you know, some of the points might be something like 70% one flower and 28% another flower and 2% another flower. And you probably just said, you know, which one has the highest value? That's going to be its class assignment. Okay, and that's basically how I'm coloring the points. The points are colored based on the highest probability, but in reality, everything gets a probabilistic assignment. Okay, everything gets a probabilistic assignment. So you know, these ones are like 99.99% belonging to the black cluster. Okay, but as I get further away, it, you know, this becomes closer to, you know, 50, 50, 51%, 49%, 49%, 51%, some kind of mix there. Okay, but again, when I'm coloring them, I can only pick one color. But you have to keep in mind, everything has a probabilistic assignment. Everything. So technically, this is probably something on the order of like 10 to the negative 15 probability of being assigned to the red cluster, but it, you know, technically non-zero, right? So so that's what we have, and then so that's what I've written on this page. Okay, so on the next slide, what we're going to do, what you're going to see is all of these things are going to get recalculated. Okay, we're going to recalculate the centroid based on the points that are probabilistically assigned to the green cluster. We're going to recalculate the centroid based on the points that are probabilistically assigned to the black cluster. We're going to recalculate the centroid based on the points that are assigned to the red cluster. Okay, and we're also going to recalculate the variance covariance matrices, and that will get reflected in the shape of these ellipses. Okay, so when we're probably going to bring this cluster, the centroid, down to somewhere somewhere around here. Okay, and when we do this, we're going to say, all right, what is the variance, right? And we need to find some kind of variance of the points that belong to green. Okay, which and again, it's probabilistically belonging to green. So we're going to kind of calculate the variance here, and again, it's going to include some of these points here. Even though they are colored black, they are probabilistically assigned to green. Okay, so so when we do that, just right away, everything kind of immediately in the next iteration, things change drastically, right? So here, all of these points are assigned to black, and we're going to recalculate the variance of all of these points that are probabilistically assigned to black. Okay, and so when we do that, you know, the variance gets huge like this. Okay, so this is after one iteration. I guess what I could do is I could have separated the E and the M step, but and then immediately what we do is we reassign points based on these things. So based on this recalculating kind of where the ellipses are, we recalculate the probabilistic weights. Okay, and again, here we've got green and black, but again, they are probabilistically assigned. So this is probably 51% green, and these ones are probably 49% green, but they just get colored black. So so we adjust them, and then we redo the variance matrix. Okay, so now that we see, okay, we don't have points way out here, you know, my variance matrix doesn't have to look like that. Okay, and so in the next iteration, the variance matrix reflects basically the points that are probabilistically assigned here. Okay, and then again we redo our membership weights, and it's iterative, so we're going back between membership weights, basically our assignments, and we recalculate the centroids and the variance matrices. Okay, and so with each iteration, things kind of improve, and we get something like this. Okay, so it started off like this, and then we get something like that. Okay, and if I allow this to keep running, eventually it converges to something around here. Okay, and this is the kind of the final cluster assignments after running the EM algorithm for quite some time, right? And so this is what we get. Okay, and if we compare these findings to the original assignments where we know the answers, we can see it did a pretty good job. Okay, and again, like k-means clustering, the actual cluster labels, which one's black, which one's red, and which one's green, is completely arbitrary. So the EM algorithm called this one green and this one red, but it doesn't matter. It's just these ones are one cluster and these ones are another cluster. Okay, and we can see it does a pretty good job. All right, so if you look carefully here, though, we can see, you know, in the true groups, that this is actually a mix of, you know, the green cluster and black cluster, right? But, you know, when the EM algorithm runs, all of these have a higher probability of belonging to the red cluster, so they get assigned to red. Okay. Again, everything is probabilistic, though. Everything's probabilistic. It's not a hard assignment that says this for sure belongs to the red cluster. They're all probabilistic. But right now, for each of these points, their highest probabilities belonging to the red cluster, and for each of these points, their highest probabilities belonging to the green cluster. And this does resolve the issue of saying a point like this should belong to the green cluster just because it's a little bit closer, right? So if you take into account the spread, the variance matrix here, you know, all of these points get assigned to green, but because it's drawing kind of the covariance there, this dot over here is not going to belong. The EM algorithm is not going to assign it to the green cluster. K-means would have assigned it to the green cluster. K-means says Euclidean distance is the measure, and so these points that are over here, you know, distance-wise, it's much closer to this cluster than this one, so they would all get assigned to green. Okay, EM takes into account the variation that exists and says, yeah, you know what, this green cluster, it's coming from a multivariate Gaussian distribution with high covariance. Therefore, points along this axis is highly likely to be generated, but this point way over here is very unlikely to be generated from this multivariate Gaussian. So it's going to get, so it's probabilistically assigned to the black cluster in the center here. Okay. Here I just started off with some different starting weights. Okay, so different starting weights. I'm going to start like this. Okay, and naturally, what's going to happen is, so when we do the initial assignments, these are the assignments that kind of happen. And again, everything is probabilistic, not it's not just green and not just red. Again, the plots are misleading in that I can only color them with one color, but everything is probabilistically assigned. But we see there is a concentration of points over here, and so when I take the mean of the points, the weighted mean of the points, it's going to get drawn over in this direction. So you're going to see the centroid of this get moved over here, right? And then here, and we also recalculate the variance in that moment, and so immediately in the next iteration, they get sent over here. Okay, and then once we have this, we redo our class assignments. Okay, and then the points get reassigned, and then we make refine our things. Okay, and so we can see here, you know, we had terrible starting locations, but then it does a fairly good job. Okay, And now the EM algorithm is not perfect, okay? So if you start off with terrible initial assignments, it can get stuck. It can, just like k-means clustering, depending on where you started, you can get different results. Same thing with the EM algorithm, right? It's just kind of searching for some structure, and here with the EM algorithm, we are able to take into account kind of the variance component of a Gaussian distribution, and we can say, certain clusters might have high variance, and you're going to get points way far away, and then other values, can have covariance and things like that, and you can end up getting a distribution. So if I run this, keep allowing many iterations to run, this is kind of the final result, and we can I can compare that to the true initial assignments here. So these are the true groups. And we can see the kind of the resulting groups identified by EM. Pretty similar, okay? And again, it's all probabilistic, okay? And it allows us to kind of mix in the different variance components there, okay? So it's not, again, it's not perfect, but it does a fairly good job despite, starting off with kind of some initial not so great estimates. Here, we're recalculating the centroids or the variance components, recalculating the means and variance components using kind of these weighted formulas. And again, we're doing everything using a probabilistic assignment. All right, so I'm gonna post a homework assignment for you guys that you can start working on this weekend, that will have you code up k-means clustering and the EM algorithm. And I think it's a pretty neat application. Monday is a holiday, Memorial Day. We honor our fallen troops, and so I will see you guys on Wednesday. So we'll end there. Oh, let me give you the second quiz answer. Second quiz answer is A as in apple. A as in apple for the second quiz answer. Okay, so we'll wrap up there for today. Have a good weekend, and we will see you guys on Wednesday. Okay, so we'll see you then.